Mr. Sheraz, please.
Assalamualaikum. Good afternoon. I am audible to everyone, I think. My name is Sheraz Khaliq and I am from School of Chemical and Material Engineering from NUST. My topic is predicting the quantum capacitance of copper-nickel alloys, combined approach of DFT functional theory and machine learning. Here is the flow of my presentation that will be followed. Due to the rapid growth in the energy storage devices because of the renewable devices, renewables like solar and wind, there is a efficient energy storage requires. By 2025, the storage market, energy storage market will be exceeded to more than $100 billion, and there is a need of devices that have high power density, fast charging, and long lifespan. So in this regime of storage energy storage devices, supercapacitor is one of the best devices that can be used for the high power density, rapid charge discharge rates, and long life cycles. And supercapacitor actually involves the surface adsorption, that is basically the fast redox reaction on the surface of the electrode. Unlike batteries that have slow periodic reaction, that is because of the electrochemical reactions within the batteries. Here is a comparison between the batteries and supercapacitors. You can see the power density of supercapacitor is much higher than the batteries, and if you see that in batteries, the charge discharge or electrons transfer is due to the electrolyte, electrons movement in the electrolytes, while on the other hand the supercapacitor charge discharge happens on the electrode material of the supercapacitor. But there is some limitation, and the limitation is the quantum capacitance of the supercapacitor metallic electrode, and this quantum capacitance comes from the density of states. Density of states is actually the states that are required for an electron to for a free electron that can be used, or that can be used in the supercapacitor electrode devices. So copper nickel alloys are the promising electrode because their composition from x is equal to 0 to 1, 0.01 to 0.02, 0.33 and up to 1. So here is a density of states of pure copper metal. You can see that the density of states is the function of the energy, applied energy in electron volts, and at the Fermi level, of the copper, the density of states are low, but the Fermi level of the nickel metal, the density of states are higher. So we can tune this copper nickel alloy system to a point where we can get the maximum density of states, and in the end we can get the higher quantum capacitance as per se. As we can know that experimental density of states can also be computed from experimental techniques as well as the computational methods. That is, a density functional theory is costly because we have to do a DFT calculation that requires more than 2 to 3 days for each composition from x equal to 0 to 1. So there is a need of a predictive model, that is machine learning. In this context, the solution is principal component analysis, which is also unsupervised machine learning method, and also the machine learning method, that is a linear regression. First, we had to dimensionally reduce using the principal component analysis method, dimensionally reduce the high dimensional data, that are the density of states of the DFT simulations into principal component that defines the whole variance of the data. and these principal components are equal to the transpose of the covariance plus the transpose of the mean of the data and the eigenvectors. Our data set will be included composition X, that is from 0 to 1, and the latest parameter from that is coordination number, mixing factor, and d orbital electron. As you can see, the basic factor in density of states is the d orbital. So we have to include this factor, d orbital electrons, in our data set. After getting this data set, we will train the linear regression model on the PCs that is calculated from the density of states and to the data set to predict the density of states and eventually the quantum capacitance of the unseen values of X. Here DFT, here is the flowchart. From DFT we can get the DOS, density of state extraction. From there we can get the principal components and then apply the machine learning training method, predict the DOS, and calculated the quantum capacitance. So this method actually reduces the computational cost and rapidly screens the alley of the composition from 0 to 1. Here are the results and discussions. Crystal structure, we have basically five, copper and nickel as a pure metal, and then these are the structure which has 25% of copper, then 75% of nickel, then 75% of copper and 25% of nickel, and 50% copper, 50% nickel. This star represents the testing alley. So if we get the data and train our machine learning model on this data, and we test our learning model, that is it actually predicting the quantum capacitance up to how much accuracy. And these are the setups. First, FCC 2x2x2 supercells with periodic boundaries and special quasi-random structures that are this random structure actually naturally model the natural randomness of the atoms in any crystal. Then we apply the first principle DFT from WASP, that is Vienna ab initio software simulation package with generalized gradient approximation with PBE functional. Plane wave basis set were expanded using kinetic energy cutoff 520, which means that if any electron that has the energy less than 52 electron volts will be simulated. Then we have to relax these these atoms or ions until the forces on each atom due to their internal effects or internal interactions less than 0.01 electron volt per Armstrong. And then there is the K point mesh of the Brazilian zone is 8 by 8 and 8. So these are the basic inputs for the DFT in WASP to do the simulation on the input metals as well as the input structure as well as the testing structure. After doing the density functional DFT on these copper nickel alloys, if copper is only one, you can see these are the curves that density of state that are the function of the energy on the copper level, showing very low density of state at Fermi level. But when the inclusion of the 25% of nickel, the density of states at the Fermi level is increasing, and after 50 it increasing much, then up to 100% of nickel and 0% copper. But we didn't know which composition is best for the density of states. So, and this is our testing alloy that can be used to test our model. Actually, we applied the machine learning model on these five density of states to calculate our principal components, and eventually the principal components will be used in our data. Here is the data generation. This is our compositions that are used, and each composition is showing its d orbital electron occupation ratio that can be described as, and then there is a coordination number of each composition, and then there is a mixing factor, and we calculate these ratios for the desired composition, and also the density of state that we can calculate from the DOS principal component that we can calculate from the DOS. And for each composition we will consider 4 PCs. That 4 PCs actually defines the whole variance of each DOS and reduces the unwanted noise, so we can concentrate over all the process. And here is the predictive results from machine learning model and PCA, and this is the density of state for upward spin up direction. 95% of accuracy was achieved, and this is the spin down density of state for, and 93% of accuracy was obtained. And you can see we can also calculate the density of states for other 100 alloys composition from X to X0 to 1, that is from 1% copper to 100% copper and 0% nickel to 100% nickel, by using the calculated PCs we calculated earlier. And here is a video demonstration how these composition are actually affecting the density of states at the Fermi level and eventually and then the quantum capacitance. These results are actually showing the actual DFT results, and these results are the predicted ones with the accuracy nearly about 94% if we calculate both up and down. So we add up and down, spin up and spin down density of states to calculate the total density of states, and then we can calculate this, and for each composition we can calculate a different quantum capacitance, and by analyzing the 100 quantum capacitances of the 100 compositions we can figure out which composition is best suited for a supercapacitor electrode material. And as per the literature review, the curves with different height peaks show asymmetry, and asymmetry curves show actually relatively maxima and the higher capacitance in one bias direction. And it is because the uneven DOS above and below and shows the tailored structure, while the same heighted peaks indicate the lower overall maxima and electronic structure. After analyzing all of the 100 curves, we can say that the composition, which includes copper 39% and nickel 61%, is the best suited for the supercapacitor electrode. Conclusion that DFT showed composition dependent quantum capacitance in copper nickel alloys with composition dependent, that will be, and machine learning with PCA reduces the computational time from 3 to 4 days of, it can more than 4 days, but on average 3 to 4 days of one composition of DOS calculation to 1 minute of prediction. And so copper 39% and nickel 61% exhibits the maximum quantum capacitance, about 20 microfarad per centimeter square. If we keep the error in mind, that is plus minus 6%, then this range of compositions are the potential electrodes for supercapacitors. And this method is actually potential for higher performance supercapacitor in energy storage, and also bridges the theory and application. These are the acknowledgments. I use the Vienna ab initio simulation software package under the commercial license. Then computational resources were used from School of Interdisciplinary Engineering and Science, NUST, and of course the audience. These are the references and I hope. Thank you so much.
Enjoy yourself. Questions, please.
It was very illuminative talk. The compositions which you have shared
Yes, yes.
in getting the quantum mechanics worked out, how did you do that? Did you have the facility to have these alloys melted and samples prepared?
Composition of crystal structures?
No, alloys, the basic alloys. Basic samples which you got.
No, I modeled these alloys in Vista, that is used for the modeling software that can model the basic crystal structure of any composition you want to simulate in DFT.
Can we use the same knowledge in getting facilities developed to analyze the to sort out the materials for recycling?
For
recycling. मटेरियल जो है वो A होगा, B होगा, C होगा, D होगा. Let me clarify the question. क्या हम कोई ऐसी facility बना सकते हैं जो आपने knowledge share किया है, जो sort out कर सके से एल्यूमिनियम स्क्रैप को, निकल कॉपर स्क्रैप को, ताकि हम इसमें उसको properly recycle कर सकें?
Yeah, it can be done, but for a machine learning perspective, you need some data to input first. If we have a data like in curves or in any kind of numbers or any type of numbers, we put that data into our system and it can predict the outcomes you wanted to know that would be the best for the given example. Yeah, it's in research phase. It's the first attempt I think I made in application of supercapacitor, but you can apply it in other applications as well, like lithium-ion batteries or in scrap metals, or the application you are saying in energy storage, other methods also using this kind of methods to do their research. It can be applied.
Practically, these alloys can be prepared in induction melting under high vacuum condition. Practically, these alloys can be prepared in induction melting through vacuum. Induction melting system.
Yeah, induction melting system it's totally the...
Because in oxidizing condition, you can't prepare the nickel containing alloy.
For experimental perspective, you need to follow the experimental procedures. For like if I use copper nickel to experimentally prepare that copper nickel, you have to use, I think there are milling methods, there are some furnace methods that can be used to actually experimentally prove this method is viable or not.
We have this small facility in our university, NED Engineering University. If you want to, in future,
of course, I would like to do this.
Welcome. So up to 5 kg, up to 10 kg, we can.
Yeah, I can give you on the basis of your requirement, I can give you the best suitable combination of materials that you want to use in your application, and you can apply them in the lab or experiment. It can be done, and it can also be verified, validated as well.
Indeed. Thank you.
So, any more questions?
Very good presentation. I have one question. Like you said that you have predict the composition that gives the best performance among all of them. Did you verify it? Like it's a predictive model, that it can possibly give the best performance. Then it is also a chance that how much accurate your model is.
Yeah, there is also some limitation that we in machine learning perspective say overfitting. To reduce that limitation, you can actually put a lot of data, multiple data. I used a simple data that you can see. This is my data set. You can add other data columns here, like if you have d orbital, if some sp, d, f orbitals or other orbitals, you can add other type of columns that are related to the motion of electrons around the atom.
Don't you think it is a little less amount of data for predictance, like you have a very few number of configurations and so do the columns, number of data points?
Yeah, these are the data points. Actually, these are the data points, and we can increase this data. But for the starter, this is
the more the data points, the better will be the predictance and the accuracy.
Yeah,
of the
if the data is larger, then the prediction is also very much fitted,
So basically,
not overfitted.
you basically didn't have verified that you have only predicted that it
Yeah, I
is- can be-
predicted it and verified it through the DFT perspective, not for the experimental point of view.
Okay.
But you can predict it from the
You didn't
DFT.
synthesize it and verify it
Yes, yes.
experimentally. Thank you.
We have time for more questions.
So you assume that you have a face-centered cubic structure,
Sure.
and on a lattice side either there is a copper atom or a nickel atom.
Yes, yes, yes.
Now in reality it is not like that.
Yes.
There are vacancies,
Yeah,
and there is a equilibrium concentration of vacancies at every temperature that you select.
yes.
So what will happen if there is a vacant site?
For this, you have to add that aspects as well in the data point that can also be added in the form of numbers, so that machine learning can predict more accurately. But on this, I used average method, like I apply an average of let's say one side of this side has potential that is the average of the whole cube. Or
What I feel is done is that you have atom A next to an atom A. So there is a bond energy.
yes,
Then you have an atom A next to atom B and a bond energy.
yes, yes.
When there is no atom, then there is something different.
There's something different. There's a vacancy. So that's why this thing is designed. So like F mixing factor that actually that can actually be applied on the vacancies as well. Like there is a copper nickel bond, you can add a total number of all bonds and also include the vacancy here as well. It's up to you that how much you put in the model or the learning method to predict. But this is the basic that can be done to our DFT calculations and then for the experimental point of view.
Thank you. Thank you. So we'll come to the conclusion of this session. Thank you for all the speakers.
Thank you, chairs. Now it's time for tea. After tea, exhibition.